Hello and welcome to my quick 5-minute presentation on valence shell electron pair repulsion theory. Now, VSEPR theory is the theory that helps explain the shapes around molecules that we see. In order to understand VSEPR theory, we must first have an understanding of Lewis structures. Now, here are some. Here's water, where we have our oxygen, 2 hydrogens, 2 covalent bonds between them, oxygen's 2 lone pairs. Now the way you construct this is oxygen's got 6 valence electrons, you'll have 1, 2, 3, 4, 1 in this covalent bond, 1 in this covalent bond. Now the hydrogens will have 1, so they'll provide 1 electron too. There we go, got our 2 covalent bonds. Here is carbon dioxide, same story here, however we've got double bonds involved here. Carbon with its 1, 2, 3, 4 valence, and oxygen with 1, 2, 3, 4, 5, 6 again. There we go. Boron trifluoride, same story again, got the lone pairs displayed. And ammonia down here, nitrogen with 1, 2, 3, and then 4, 5 in its lone pair, and then 3 hydrogens. Now, how do you draw a Lewis structure? Well, I'll give an example of our good friend CH4 methane. Now we're going to start with our central atom, carbon. Carbon has 2, 3, 4 valence electrons. We'll have 4 hydrogens, each one of these having 1 valence electron to its name. There we go. And then they will join up, make 4 individual covalent bonds. And there is our Lewis diagram of methane. Now, Lewis structures are important for VSEPR theory due to how it can explain the amount of electron domains around a molecule. Sorry about that. And an electron domain will be an area of negativity caused by electrons, obviously, and that will be either a lone pair, a lone electron, or a bond. So here's water, it has 1, 2, 3, 4, there you go, 4 domains. Carbon dioxide, 1, 2, boron trifluoride, 1, 2, 3, and then ammonia has 1, 2, 3, 4. Now, the shapes that come of having these electron domains are as follows. If you have 2, you'll have linear electron geometry, which will be bond angle of 180 degrees. Now 3 will be trigonal planar, that is 120 degrees. These angles come about because the negative electron domains will want to be as far away from each other as possible. However, they're still locked together via that central atom. So this is just the angle corresponding to the furthest distance each electron domain can be from one another, whilst also being joined to the same thing. Now, tetrahedral will have bond angles of 109.5 degrees. We'll have trigonal bipyramidal electron geometry if we have 5. I'll explain the bond angles on those in just a second. And 6 will be octahedral, which is all 90 degrees, and I'll show you that now as well. Now, for examples of shapes that correspond to electron geometry, I have a couple here. We have carbon dioxide. As you can see, we have our double bonds, oxygen, carbon, 2 electron domains here, linear geometry for it to align, if you can see that. Now, for a 3 electron domain, I have an example of, say, boron trifluoride. So here we go, 120 degree bond angles. There we go. Everything is as far away from each other as it can possibly be. It's nice and happy. Now, moving up to 4, we have tetrahedral. As you can see, everything is as far away from each other as it can possibly be. If you had to measure these angles here, you'd have 109.5 degrees. Now, what if we have something like phosphorus pentachloride, say? which has 5 around it. Now the furthest away everything can be in this is to have a trigonal planar arrangement around here, as you can see, it's planar, and then to have this axial shaft here, which will form 90-degree angles to your trigonal planar almost ring around it. It's almost as if it's a space station or something. Now you'll have your 120 degrees, you'll have your 90 degrees. And here is an example of octahedral, say, I don't know, sulfur hexafluoride. Everything's got 90 degrees. Lovely. Everything's as far away and happy as possible. Now, some things, as you saw earlier with the example of ammonia, will have 4 electron domains, yet only 3 atoms bonded. Here's my ammonia here. Our lone pairs are being demonstrated by this murky blue tack here. Now, you'd think it's only got 3 electrons, so it might be planar, but it's not. And it's not trigonal planar, it's not tetrahedral either, for you see lone pairs are smaller and more close to the atom, therefore will provide a much more, well, I say much, not a great deal, but will provide more repulsion than a bond will. Therefore, in something like this, which we call pyramidal, you'll have bond angles of about 107 degrees. Now you'll also get things like water, which I don't have a model of, but I can draw you. So we'll have our oxygen, about 2 lone pairs in the oxygen. We'll have hydrogen down here, a hydrogen down here. Now, the way I've drawn this is kind of misleading. So you see this lone pair will be heading into the paper, and this lone pair will be heading out of the paper, which will give it an electron geometry of tetrahedral. However, the shape of things we can actually see, not the electrons, will be called V-shape. And that will have a bond angle of 104 degrees. And this is because you'll have the 2 electron lone pairs repulsing even more, and thus squishing the bonds together. For they will have less repulsion of each other, and these will of each other, and these will of the bonds. I hope that my presentation has made sense to you. I hope it might have helped. For further reading, you can check in your Chem Cubed. I believe the information is about 234, page 234. You can also refer back to your videos made by Simon, and there's plethora of information online. I got information on bond angles used and information on the Lewis structures from the IUPAC website, which I've found to be quite a good source of information, albeit quite difficult to find the information on. Yeah, I hope you have a good day.